Okay, so good morning and welcome to the PhD defense of Peter Caristo from the Department of Environmental System Science here at ETH in Zurich. It's a pleasure to see so many faces, and it's of course a great and important day for you. My name is Väitöstilaisuuden. I will be chairing this defense. I have nothing to do with this work. I know nothing about plant pathology. I'm an atmospheric scientist, and the only thing I'm doing is making sure that this follows the procedures as usual. I would like to welcome and introduce the committee, in particular the Professor Emerson Del Ponte from the Universidade Federal de Viçosa. Did I spell this correctly? Thank you very much for traveling this far and for taking the time to examine this PhD. This is an important task. We do rely on outside independent expertise to make sure that the quality of this work is adequate. So you get the most time for questions as a reward for traveling this far. Then Alexei Mikoverite, if I get this right, also from our department here, who supervised the PhD, and Bruce Bandol, who is the doctoral father of this defense. The way this works is we'll have a presentation from you, 20 minutes or so, followed by questions from the committee and questions from the public if there are any. So the floor is yours.
Thank you. So good morning everyone, and welcome here. It's really wonderful to be here and see all familiar faces in the audience. I also like to welcome Emerson very much here. It's really nice to get you here, and also welcome our audience through the live stream, so you are online. I would like to start my presentation with acknowledgements. First of all, I want to thank my supervisors, Alexei Mikoverite and Bruce McDonald. I've said lots of positive things about you. I have got a lot of support from you for myself and my ideas, and freedom to follow my ideas. It's been great. I also want to thank all the collaborators. In the first chapter, we collaborate with Andy, Kang, Jonas, and Akin from ETH's Crop Science, and Fabio from Agroscope. In the second chapter, we had wonderful master student Susanne Dora in our group. In the third chapter, Frederick and Sandrine from Indra Biocell, close to Paris. And in the fourth chapter, we collaborate with Sarah, Moes, Hayer, and Amor from Tunisia. I also want to thank all the plant pathology people and also my lovely family for all the mental and practical support during my doctoral studies. The main topic of my doctoral work was Setoria triticid blotch. It's a disease that is most important on wheat in Europe. And wheat, in turn, is the most important crop in Europe. The annual production value is 33 billion. But if you look at this pile, you might notice that something is missing from the top. The farmers use an extra billion every year for fungicides that they are spraying on the field. And despite that extensive effort, the disease is still causing losses of about 2 billion euros every year. So this is how the pile could look if the SDB was not around. But that's not the case. We are losing the money. Now, how does the disease make this economic damage? SDB, Setoria triticid blotch, is a fungal disease. It's caused by fungus, Setoria triticid. And it's visible in the field in these brownish or yellowish lesions that appear on wheat leaves. And by damaging the leaf tissue, it reduces the yield production of the plants. How the disease works? There are spores that land on a wheat leaf. On a wheat leaf, they germinate, they grow hyphae, and then that hyphal string finds a stomata where it can penetrate inside the leaf. Then it grows inside the leaf and causes this symptomatic disease after about 10 days. If you look here, you see fresh wheat leaf tissue collapsing and turning yellowish and brownish in this time-lapse video. So this is how the disease looks in a little bit faster mode. You also notice these dark spots. Those are called pycnidia. They are asexual fruiting bodies of the fungus, so they produce clonal spores. And those clonal spores will then splash around with rain and cause further disease. If you look more carefully to young lesion, you see some young media, these little green bubbles. And if you look them, you see how they start oozing. They push out transparent or crystalline masses of spores, and those spore masses will cause the further disease. You see the spores are coming out like that. So this is how the disease looks in small scale. In more broad scale, generally, we can describe the disease dynamics with epidemic cycle. Epidemic cycle gives the seasonal dynamics of the disease. From the top you see it starts with initial infection in young seedlings. With winter wheat in Switzerland, it would be around October, November at earliest. Then there is lesion formation, as you saw. There are putlidia produced within the lesions. Then these clonal rain splash dispersed spores. And there can be multiple cycles of clonal reproduction and infection during the season. And that will lead to the devastating epidemics that you see in the figure in the bottom. Later in the season, there is also sexual reproduction. The fungal strains mate and produce sexual spores. And those sexual spores are a little bit different. They are wind dispersed, and they are also more resistant against the environmental conditions. Those will contribute to the epidemic in the same year, but they will also act as primary inoculum for the next season's epidemic. So those wind dispersed sexual spores will survive over the period from harvest to emergence of a new crop. And they will start infecting the seedlings. And it's really important for us to be able to understand how the disease works in season scale, and also more precisely in which conditions and how it works. So for example, in terms of weather, what the disease needs, what kind of temperature, what kind of rainfall. Because when we understand what the disease needs, we can try to remove those conditions. So we can try to make conditions if we can affect it, so that the disease is not thriving. And also, if we know that the conditions, environmental conditions, have been really good for the disease, then it makes sense to, for example, spray fungicides to control the disease. If the conditions are not good for the disease, there is no need for control. And this leads to the main target of my thesis work, which is to improve control of Septoria triticum blotch. We had different objectives. First, we wanted to characterize resistance of wheat cultivars against Septoria triticum blotch. Second, we wanted to measure epidemic parameters with high precision. These two objectives first will lead to improved understanding of what we have in hand for controlling the disease. And the second will allow us to understand the disease dynamics more precisely, probably do more precise models of the disease dynamics to predict the disease, and also try to understand it better for helping our management. And in the third step, we would like to improve the control with some kind of clever strategies. So, in the first chapter, we had the objective of characterizing resistance of wheat. So we measured quantitative resistance of wheat cultivars. We had 335 wheat varieties growing in a field, and they were naturally infected by local Gymnoseptoria population. We went to the field and collected in total 22,000 leaves, and we sticked them on those paper sheets, scanned them, and got high quality images of the leaves. Then we used automated image analysis to measure disease severity on those leaves. In the image analysis, we took the leaves and analyzed it for different traits. First, we have kind of a traditional trait of disease severity, which reflects host damage. So what is the proportion of the leaf tissue that is damaged? Some cultivars might have small lesions or small number of lesions. Some of them might have larger or higher number of lesions. In total, we had 37 square meters of leaf surface that we analyzed, and 11 square meters of that was damaged, according to our image analysis. But thanks to the image analysis, we were also able to measure smaller symptoms, those pycnidia, the dark spots. Here we could detect those dark spots within lesions, and we found out that in some cultivars the pycnidia are with low density, they occur with low density, and in some cultivars with higher density. And this pycnidia density is important for the pathogen. It reflects the pathogen reproduction, and it also reflects the potential for consequent epidemics. So how many spores the disease the fungus is able to produce for further infections. In total, we counted around 3 million pycnidia on those leaves. So you can imagine that with manual counting it wouldn't be possible, only to this, thanks to this wonderful image analysis. So now we wanted to characterize the wheat cultivars based on these traits. First, host damage. The x-axis reflects the host damage values, and the individual blue spots are for individual leaves. The sigmoidal curve, the S-curve, gives the mean values of each cultivar. So there are gray and colored points for mean host damage of each cultivar. And those cultivars are now sorted according to the host damage levels. So that in the bottom, we have cultivars that have on average low host damage. And higher up, we have those cultivars that have higher average host damage. So it's good to be in the bottom and bad to be on top. And now we did the same thing with pathogen reproduction. Again, we have measures of pathogen reproduction on individual leaves. We have means of each cultivar, and we have ranked the cultivars according to the pathogen reproduction. In the bottom, there are cultivars with really low density of pycnidia, so those cultivars are allowing for low levels of pathogen reproduction. Higher up, we have cultivars that have really high density of pycnidia on their lesions, so they are allowing for higher levels of pathogen reproduction, which will then allow for faster or stronger epidemic development. And now, the natural question was, of course, what is the connection between these two rankings? Can we predict levels of pathogen reproduction based on host damage? And it turned out that the connection is really not very strong. When we take 30 most resistant cultivars measured for host damage, so the most resistant cultivars against host damage, and map them to the ranking on pathogen reproduction. We have some cultivars that keep their good ranking, they stay in the bottom, but we have really many cultivars that jump to the top of the ranking on pathogen reproduction. Which means that those cultivars have really low host damage levels, but they have really high density of pycnidia within the lesions that will occur. And also, other way around, when we took the 30 most susceptible cultivars against host damage, those that allow most damage on the leaves, some of them will be susceptible also against pathogen reproduction, but some of them were really good against pathogen reproduction. So even though there were large lesions, there was really low density of pycnidia within those lesions. So in the first chapter, we came to the conclusion that there are two types of resistance. One type of resistance is against host damage, and the other type is against pathogen reproduction. So that is kind of the main result or highlight of the first chapter. Now I will also show little highlights from the other chapters. In the second chapter, we move to the second objective of measuring epidemic parameters. And here what we measured was infection efficiency, which means the probability of infection of spores. We took aluminium plate where we put healthy living leaves, and we flattened them on the surface, and then we sprayed those plates with spore suspension in different densities or different concentrations. After spraying, we took those reference membranes between the leaf sets, and we were able to determine the density of spores that we were actually spraying. So there were some variation in the spraying procedure, but because of these references, we were able to measure it afterwards, what actually ended up on the planes. Then we took photos of the leaf sets every day and counted lesions to get the total number of infections. And this work was done, the practical work was mostly done by Susanne and Nora. So when we look at the connection between spore density and lesion number or lesion density, with low spore density, we have practically no disease. With medium low density, we start to see some lesions appearing. With medium high density, even more. And with the highest density, the leaves were totally infected and destroyed quite fast. And from the scope of that connection, so how much spores was required to create certain increase in the lesion numbers, we determined that the infection efficiency was 4% in our case. In the third chapter, we measured another epidemic parameter, spread of the disease in the field. We had elongated plots like this. In the middle, we had the inoculation area where we sprayed spore suspensions of different strains. Then we went to the field and inspected the disease levels in the inoculation area and also outside of the inoculation area on those light orange measurement lines. We again collected the leaves for measuring the disease severity, but we also used genotyping. We isolated some strains and we used strain-specific PCR markers that we developed for detecting our strain. When we sprayed our strain in the inoculation area, we were able to confirm that it was our strain that was spreading out on the plots, and we were able to differentiate between our strain and the natural background infection from external sources. As a result of the phenotypic characterization, so the disease levels that we observed, first on the left we have differences in the inoculation area. So one strain, the green one, 3D7, was producing more pupillia than blue one, 1A5. And then after one spread event, we measured the disease gradients. They were quite beautiful, I would say. You see clearly that close to the source, we have higher levels of disease, and further away from the source, the disease levels go down. And the red line reflects the disease levels on uninoculated control plots. So it's kind of natural background level of infection. So in the furthermost points, the disease levels were down to natural level. Probably there was no contribution from our source anymore. We genotyped some strains and also got the same pattern. At the closest measurement point, we had around 80% of the isolated strains being our own, and only 20% from external sources. But further away, only 30% of the infection was from our strains, and most of the disease was coming from external sources. And now, when we fitted the model to the phenotypic data, we were able to characterize the spread and come to the conclusion that when spreading from a single point source, the disease will create certain pattern, and 99% of the new infection that is caused by the spread from that source are staying within 1 meter distance from the source. And finally, in the fourth chapter, we started to implement some clever strategies for controlling SDB. And here the clever strategy was cultivar mixtures. We had 3 cultivars, susceptible Karim, the yellow one on top, and then 2 resistant cultivars, Salim and Monastir, blue and green. The experimental design was made so that we always had Karim in 0, 25, 50, 75 or 100%. And then we complemented Karim with either Salim or Monastir or their combination, their mixture. So we put a certain percentage of the resistant cultivars. So for example, here we have 25% of Karim and 75% of Monastir, and then 75% of Karim and 25% of Salim. Probably not for a surprise anymore, we went to the field, collected the leaves and used the automated image analysis for measuring the disease levels. And when we look at the disease level data from those mixture plots, we were really happy to see quite clear results. Here in the plot, all of the treatments are pooled based on the percentage of resistant cultivar. On left, we have 0% of resistance, which means the susceptible cultivar alone. Then we have 25% of resistant cultivar added to the susceptible, 50%, 75%, and 100%. So at the end, we had only the resistant cultivar alone. And when you look at the disease levels that we measured, you see clearly that the susceptible cultivar alone had higher disease levels, and all of the mixture treatments had lower disease levels, and those were not significantly different from each other. And this gave us a really nice conclusion that already 25% of resistance in the mixture is enough for suppressing the disease levels as much as the resistant cultivar alone. We don't need to show entire field with our resistant cultivar. It's enough to put on 1/4 of the seeds being resistant, and the rest can be susceptible. So, to summarize these highlights from my chapters, we observed these two types of resistance against host damage and pathogen reproduction. We measured 4% infection efficiency and around 1 meter spread of the disease in field conditions. And finally, we found out that 25% of resistance is enough for suppressing the disease very efficiently. As a conclusion, I would say that epidemiology is really useful. Of course, I love it. And I think that there is great potential for further improvement of plant disease management. Thank you very much.